Today we're going to be discussing the Trane Centrifugal CVHE and CVHF series chillers. So let's just start with the basics. End of the day, you have an evaporator, you have a condenser, right? Everything's still the same. This is your suction line coming into the compressor. It comes in the compressor. On this other side over here, it's going to come out into the condenser. These heat exchangers are known as barrel heat exchangers, or specifically like this is a flooded evaporator design. Now there are a few other designs out there that do exist, such as falling film and hybrid type evaporators. York is a lot more common to use those, but this is just a basic flooded evaporator setup. And what that means is all your refrigerant, it just sits inside of the bottom of this barrel, and it's in the refrigerant is pushed into the bottom ports. On the back side of this evaporator, there is a port with a flash plate coming in that is feeding refrigerant into the bottom of the barrel. And then we just maintain a certain liquid level in the bottom, and all that's calculated in. It's not mechanically metered on these particular machines. And the refrigerant gets pulled back into the compressor from there. You'll see that they do have this little distribution plate. The reason for this plate is so that you've got this big suction volute coming through. You really want to distribute all of the pull across that liquid refrigerant evenly. That refrigerant's going to be below that plate level, and so you're going to have all your liquid refrigerant below that. Anything above that pulling through is going to be all vapor. And what can happen is if that plate's not there to distribute it, it will cause the refrigerant to kind of collect or pull more heavily right here in this one spot, and you won't get an even distribution or evaporation throughout the entire barrel, which then just heavily impacts efficiency. It impacts everything. It's not what we want. It's not what we're looking for. So anyway, this distribution plate allows that, and really all it is just a screen mesh. I do have some teardown videos I've done where I've kind of shown what that mesh looks like. So if you can go check those out, see what they physically look like in person if you've never seen one. The refrigerant is on the outside of the tubes in this particular case, and most all of your water-cooled equipment, it's going to have the refrigerant on the outside of the tubes when they're using a barrel. Now, some of the air-cooleds, that is the other way around, and I explained some of that in the YCIV refrigeration cycle video, and the fact of many, and Trane's the same way in this way on their RTAA and other series, is most of their especially older equipment is going to have a DX barrel, and so these are not that way though. These are flooded. I'm not going to dive into that here. I've talked about that in a number of other videos. Regardless, your water is going to be what's on the inside of the tube. So this little shiny pieces here, these are your physical copper tubes that go through the heat exchanger, and that's where the water sits inside. That's what we take a brush machine and do routine maintenance on. Anyway, we come through into the compressor. This is your relief here. Now, these machines that we're specifically discussing are still low pressure machines, which means that they're either running a 123 or a R11 on some of the older ones. A majority of your new ones are going to be 123, and the newest ones that are coming out, they are developing some other refrigerants. I'm not exactly sure as to which ones they're going to commit to. There's several that have been discussed over time, but not any of the manufacturers have outright committed to a one specific refrigerant at this time. So this relief is actually a 15 psi burst plate, and it's exactly what it sounds like. If you get this suction elbow, and many people do this during repairs, I've done it myself for that matter. You get this suction elbow above 15 psi, it's going to blow, and when that goes, it's about a $500 part most of the time. It's done. I mean, there's nothing else to do for it. When it cracks, when it ruptures, it's done. Anyway, refrigerant pulls through, comes through the suction elbow into the compressor. Now, this very first thing you're going to see right here, these are your inlet guide vanes. Your inlet guide vanes that's how you control flow through this machine. So basically, this is your load control. This is your unloader solenoid valve. This is your staging of multiple compressors. For example, say it's a two compressor machine. Well, you're going to want to run one compressor for half capacity. Well, instead of killing a compressor, we're controlling these guide vanes. Another example, if you're familiar with screw compressors, this is your slide valve, or if this is what controls the load. Just end of the day, whatever version of load control you're familiar with, this is how this machine is doing it. It's doing it through these guide vanes. And they'll just close off. They open and close, and they're just as simple as that. They're not a complicated piece of equipment. They do fail. They do have issues, and that's all for another video. But this is what's going to do it. So at the startup of this machine, these guide vanes are going to be in full closed position. If they're not, you're going to have issues. It's more specifically, the main issue that usually happens is the compressor will overamp at startup. So when it goes to turn on, it will overcurrent, and it's going to give you problems there because of the overcurrent. And that could be because, say, there's a dozen vanes in there, and one of them the armature just breaks on. Well, when the armature breaks, it ends up just causing it to it'll get stuck in a single position. Maybe it won't close like it's supposed to all the way, or something along those lines. When that happens, yeah, that's what you're gonna have. Trane is a lot less tight on their tolerances compared to somebody like York. York tells you that if you can fold a dollar bill 4 times and then make it fit between the vanes when they're closed, and York's vanes actually overlap each other. They have to be machined in. The York's chillers aren't going to do well. They're going to give you trouble, specifically like their YK and YT series. Trane is a lot more loose with that. They're not near as restrictive, and their vanes don't actually overlap. They kind of just butt up to each other. So much different design, much different setup in that way. But still, nonetheless, that's going to be a critical component to this entire machine and its calibration. And this is controlled by a little armature right here. Now, I have done a Trane centrifugal overview as well. I have 2 of them out there. The very first one, which kind of has some of my old branding on it, there was some kind of weird thing happened with the footage at export, and I didn't catch it, and so the back half of the video doesn't actually work. It's just dead space. Actually, it was kind of weird. But I did redo the video, re-release it, and made some actual upgrades to it along the way once I realized what had happened. And anyway, I will link that video in this section of the video here. But this is what controls the guide vanes, and there is 2 sets of vane controls in this machine. Just something to be aware of. I go through all this in person, on site, on the machine itself in that other video. Regardless, evaporator through the suction into the guide vanes, and then we start hitting the compressors. And from here, let's switch over to our next slide. So we'll take a couple of minutes and spend it right here. So this is just a very basic, very crude setup in a lot of ways, but it gets the point across, right? So this is essentially what's happening here. This is our evaporator. We're pulling off through the suction volute. These are your little guide vanes right here. This is your impeller for the compressor. And then we're coming out the discharge back into the discharge line, into the condenser. We then take and use the condenser water to condense the liquid down. We come through an orifice here and then back into the evaporator. I'm not going to spend a whole lot of time on this. This really is, they function off the same basic design principles every machine runs from. But again, it just some sort of visualization to that might help with the rest of this process. From here, this is our suction line coming in. Okay, so from that other example, we're going to talk a little deeper into the actual cycle of the system at this point. So this is your evaporator. We're pulling through the suction volute, through the guide vanes. They're going to be located right here, and into the impellers. Now there's 2 impellers here, and this is where Trane has a very different approach than many manufacturers. So somebody like York uses a high-speed design, and I believe Carrier does as well, where they have a bull gear setup. We've got a low and high speed gears, and they're running the one impeller, and usually a smaller impeller at that, to move the same volume of refrigerant From experience, though, it's a great design, it's a great theory, but those do have a tendency to have a lot more trouble with surging and things. That's one prop I will give to Trane, is they have a very solid design that is just it can take a beating pretty good, honestly. I see a lot of them very mistreated, and they just keep working. But theirs is a what's considered a low speed design, so they have very large impellers, especially compared to the other manufacturers, and they use multiple of them. So they stage their impellers in such a way to where they can run this motor at a standard speed. I think it's either like 1800 or 3600 RPM, like a general motor speed you would have on any typical commercial motor. It's nothing fancy. But they can do that and still get the same amount of volume and flow and things and efficiency through these impellers and the multiple staging of them. And so stage 1 impeller feeds stage 2 impeller, which then is your discharge line coming back out of the compressor into the condenser and then back through. Again, this is not a super complicated process. At the end of the day, I'll talk about surging and things a little bit deeper into the video. We won't go into it right this second. But it's not as complicated as it looks. It's big. It has a lot of extremely tight tolerances. And so where people get in trouble is understanding, the tolerances that are required in order to keep this machine fully functional. That's where people get in trouble. But the actual concept of the design is not the complicated part. It's not the hard part. The design itself is honestly pretty simple. We come into the condenser. So the condenser is just a standard everyday condenser, right? There's nothing really fancy going on here on a Trane machine. We're just processing water through pipes. It pulls the heat out of the refrigerant that and then sends it off to a cooling tower. Anyway, coming out the bottom of the condenser here, this is where Trane gets a little more interesting. Coming out the bottom of the condenser, we have our liquid line, and you're going to go through a first stage flash, okay? So this is just a flash plate coming into what is known as the economizer. So that big black tank on the side of the Trane chillers is your actual economizer. And this is, like I said, this is just an orifice plate, okay? It's the same exact concept as any other orifice. It's just this is a literal plate that has basically a lot of perforations in it, so that it can just restrict the flow and create that pressure drop, which it enables the flash. Okay, so that's what we're trying to do. We're trying to create a pressure drop, which is what any metering device does, and it makes the refrigerant flash due to the pressure drop. So what always happens, TXVs are the same way, or any metering device. When you have that flash, you say, I use 80-20% rule, right? So 80% of the refrigerant stays liquid, and it actually subcools even deeper. All right, so say it was 5 degrees subcooled here. Well, it may come out the other side of the flash plate, 10 degrees subcooled, and the heat that allowed that 80% liquid to go from 5 to 10 degrees of subcool gets trapped in that 20% of vapor that flashed off. Okay, so that 20% of vapor then comes into this economizer and gets collected at the very top. Well, there's a pipe, there's a pipe connection that goes in and bolts into the side of the compressor housing. All this is mounted on the condenser side, by the way. So from the condenser view of the unit, there's a pipe that goes up and bolts into the compressor housing and between the first and second stage impellers, and it's getting pulled into the second stage impeller suction. And so that impeller is pulling all of that flash gas back into the system to recycle it. And so yes, do we sacrifice a little bit of capacity here? Yes. That is the final answer. Anytime you use an economizer, you're always going to sacrifice a little bit of capacity, but your efficiency dramatically increases when you do a setup like this. It doesn't matter whether it's a flash tank type economizer like this, which York also uses, or if it's just a brace plate heat exchanger with a metering valve on it. all the brands use some form of carriers. Real common to use those braze plate heat exchangers for their economizers. So anyway, it's all the same basic function. Yes, you lose capacity, you gain efficiency. Vapor gets pulled back into the compressor. Then we come over, and so now we've got this 10 degree subcooled liquid refrigerant coming through, and we're going into the outlet of the economizer as a pure liquid again. Okay, so coming into the economizer, we're at that 80-20. Coming out, we're back at a full liquid state. Then we go through the final flash point, which is the second stage flash, where we then enter the evaporator. And so this flash is one, it's a lot less of a flash. So I don't have the hard numbers, but I'll use an example. Say it's a 90-10 or maybe a 95-5 ratio this time, where only 5 or 10% is actually flash gas versus it actually being the full 20%, for example. Anyway, you get the point. It comes in and it's got a very minimal flash at that point. It fills the evaporator. We chill the water back down. It pulls back into the suction, and off we go. We're running for the races. And this, again, all this is a CVHF design. CVHE does have a little bit different design. We will also go deeper into the additional components of this system, because all that's part of this cycle. Right now, we're heavily discussing just the refrigerated section itself, the main nuts and bolts of just what makes the machine operate. So here's a little bit deeper view of the CVHF Economizer specifically, or also a two-stage chiller economizer. This is the initial flash coming into the economizer. You'll see the liquid just kind of sits in the bottom of a big tank. All this vapor is getting pulled back into the compressor, and then it flows back out into the evaporator. This is just another visual representation to kind of give you the picture and just a view of what it is we're talking about and what it looks like inside. Again, I have a video where I'm in person, and I go through all of this in person, where you can see the physical components, and I talk pretty in depth about them there as well. But I wanted to do this to give you a very good inside visual. One of the things that I did not mention here that I will just throw in very quickly is there is a second stage guide vane, but it's a very different design than the first stage, and so it sits in between the two impellers, and it also looks very different. The armature that controls it is a very different design, so just be aware of that. There are two different designs, but there are two different sets of guide vanes on these machines. The CVHE series that has 3 stages, it also has just 2 guide vanes. There's not a third set of guide vanes in those, but the location kind of stays the same in the fact that the first stage and then the final stage impellers are the ones that get those guide vanes. So what you're looking at here is a 3-stage design. Okay, it's the same, basically the same picture, but there are just a couple of slight differences. Obviously, first and foremost, the CVHE series is going to have this 3rd impeller here. Okay, so you've got stage 1, 2, 3. Each of these stages feed into the next, and it's just pushing through. Again, you're going to have guide vane here. There's going to be a guide vane here, and everything else about this basically functions the same. It just has 1 additional impeller, and you'll be able to see it visually on the compressor. You can tell by counting the ribs. Basically, you'll have 2 ribs on a CVHF, and a CVHE. When you look at the compressor, you'll see 3 ribs. Each of those ribs is actually the point at which the impeller sits. The other difference in this design is here at the economizer. So we kind of take the economizer to a whole nother level. You'll notice that there is a divider plate, and there's an extra little piece down here, and there are 2 pipes coming off the economizer. This is another way to identify, am I looking at a CVHE or a CVHF? A CVHE is going to have a 2-pipe economizer coming off the top for the vapor gas. So diving into that a little bit deeper, we're coming from the condenser into the first stage flash. That flashes off. It's the same exact scenario as the CVHF. So we're dealing with an 80-20% ratio, right? So the 20% gets pulled back into the final stage impeller, okay, stage 3, and the 80% gets pushed through a second stage flash plate here inside the economizer. This is all built into the economizer. So we go through this second stage and it all flashes off. This pulls into the economizer on the second stage impeller on this other tank. And again, it's the same scenario. Flash gas sits up here, liquid refrigerant gets even more subcooled. So we gain subcooling here on this liquid refrigerant. We gain even more subcooling here on this liquid refrigerant, and then it comes back out 100% liquid, going to the third stage of flash on the final plate going into the evaporator. And this is physically located at the evaporator itself. I mean, it's all right there. Where these sit are inside of flange bolt housings. And so there's actual flanges that'll bolt up, and where that flange bolts on either side of the pipe on the machine, that is the actual point at which that orifice is sitting. So just so you're aware, usually this one is right at the actual housing of the evaporator, like actually molded into the evaporator. It might have a short stub out, maybe, or it may just be a part of the evaporator housing that was kind of molded in. This will usually have a stub out to where it'll actually look very much like this. It'll come out the bottom of the condenser as part of the liquid, and then it'll flash, and then this will come up into the economizer, and usually they'll be insulated from this point on. So, and like I said, you'll see these are, I think, like a 4 to 6 bolt flange depending on the size of the machine. Other than that, it's all the same, right? We come through the evaporator, guide vanes, compressors, all of it's the same. This is what's extra. Now let's cycle over and we'll take a look at the graphic of this economizer. And here you go. So this is the basic graphic. We're coming in first stage, come through. This gets pulled out into the third stage impeller. We go through this kind of bottom chamber here through another orifice into the second stage of the economizer, which gets pulled into the second stage impeller, and then back out to the evaporator. It's pretty straightforward, right? It seems very complicated when we can't really visualize it, and it's hard to picture what all is happening in there, and especially even the manuals can really kind of struggle really explaining this in a way that makes sense, especially to somebody that's just brand new to this entirely and just trying to figure it out. Hopefully this explanation will really kind of help break this down in such a way to where it makes a lot more sense. I wanted to show this picture for a couple of reasons. This gives a really nice graphical representation of the compressor itself, right? So this is the piece of the machine that I think tends to give everybody the most trouble in understanding. End of the day, you've got a ball bearing back here, you've got your bearing assembly up here. This front assembly does have a journal bearing, so just be aware of that, and I'll explain that deeper here shortly. This is a very accurate representation of the guide vane assembly for the first stage, and this is the armatures that you see. If you go look at my other video, you'll see these exact same armatures that control them. And these little ridges here are part of that vane assembly and its ability to control. These motors are semi-hermetically sealed, just like the depiction says. This is all part of the refrigerant stream. It's all built in, so some of the other, say York, for example, some of their centrifugal chillers, the motor's external. It's not part of the refrigerant stream. Trane does. Trane, I think also Carrier, many of their motors are also built into their stream. So anyway, doesn't matter, just something to be aware of. This is your terminal lugs. So we're talking refrigeration cycle here. So the reason I'm going to bring this up is just one, it's a really nice kind of graphic depiction, but two, I wanted to also use this as an opportunity to talk about some of the oil management as well and how that factors in. And part of that is this little flash tank right here. So this is a vent tank slash oil separator. It's got several jobs it functions in. It's more critical to what we're discussing now, and the fact that this is what prevents a lot of oil from getting back into the condenser, and specifically the evaporator. It also allows the oil tank or the oil reservoir to vent its vapor that may collect into the top of that of the tank back out into the evaporator. Another thing you can see here that's pretty nicely displayed is these right here. This little line, it may be kind of hard to follow. I'll try to explain this better later. Here, we can draw this here. This pipe right here, right there. That pipe is part of the motor cooling circuit. Okay, so this is the drain pipe that the refrigerant that gets pumped into the motor housing drains back through to reintroduce the refrigerant back into the system. And so that's something that we should talk about now. Is this is part of our refrigeration circuit on these machines, is we have to keep this motor cool. We keep it cool by pumping refrigerant into the motor housing. Oh, back over here, you can't see it from this angle, but on this side of the system, there is a third pipe that lands in between these two drain pipes that is pumping refrigerant into the motor housing, and it goes through a little flash orifice plate that pushes liquid refrigerant in there and gives some cooling to the motor, and then the additional refrigerant as it cools the motor down just flows naturally through gravity back down into the condenser side of the system. Continuation of that, all of that conversation leads us to this point. So this may look very intimidating, and that's okay. So let's break it down as best we can. So before we get into any of the rest of this, let's just first get our bearings as to what it is we're looking at. So this bottom piece of the machine here, this is your evaporator, right? You can tell this is the compressor. This particular one we're looking at, we see there's one pipe coming off the economizer. Here's the motor. We count 1, 2 ridges. Okay, so all of these are identifying this is a 2-stage machine, being a CVHF series. This is our suction volute coming in. The discharge is right over here, so this will be your discharge line. And I know all this kind of overlays, that's why I want to just give some parameters first. And then this top cylinder kind of up here, almost in the background, this would be your condenser back here. Evaporator, condenser, and compressor, suction, economizer, vent. Obviously this would be the economizer. These are the pipes. So right here is the pipe coming off the bottom of the economizer going into the economizer. Your flash plate would be somewhere right about here, and then coming out of the economizer back into the evaporator, which this here would make that flash plate there. This is your oil sump right here. So we'll dive a little bit deeper into that, but we'll finish specifically all the refrigeration side of the circuit, and then we'll talk a little bit about the oil management and just kind of how that plays a factor. So like I was discussing earlier, right here is that drain coming back into the condenser for the refrigerant after it has finished cooling the motor. That is being fed from down here. So coming off of the liquid line right here into this little assembly here at the sump. This is actually a refrigerant pump that is tied to the mechanical oil pump inside of the oil sump. So the oil pump runs the refrigerant pump to where it is pulling liquid refrigerant in, and then it pushes it from there up into the compressor housing through this little orifice plate. So this is what assists the motor in maintaining a proper temperature and cool operation, while it's running. And again, all of the additional refrigerant that collects in the bottom, and it all siphons back down into the condenser from here. But this is your motor cooling circuit. This is what your refrigerant pump is doing, and that's what those extra lines that are coming into the oil sump there, if you're ever looking at the face of one, that's what they are. It's all part of the motor cooling side of this system. The other part of this refrigeration cycle, and this is kind of the final piece for what we're dealing with, the rest of this will pertain to the oil management side, is we feed up. This is your vent right here that goes back to the evaporator. So any vapors, anything that collects in the top of this tank or the sump is allowed to process through this pipe here into this little oil separator we were discussing earlier. And then once it comes in the side, it's allowed to then just vent back to the evaporator through a pipe. So it's just piped back into the evaporator, and the low pressure side of the evaporator allows it to pull back through. So just something to be aware of is that's how the additional vapors that collect here get vented. Next, we will discuss the oil management side of it. I might end up doing a separate video on just this oil management side, just going into greater detail on it specifically. But in the meantime, we'll go ahead and cover it here because it does play a factor as part of the system. So this is your oil sump. There is a pump, and this little device right here is your oil regulator. So what it is doing is you come out the regulator through a cooler inside the economizer. So this cooler is inside in the economizer is exactly that, right? It helps process, make sure the oil, it maintains a proper temperature going into the compressor. It's why it's also important that we maintain a proper oil temperature inside the sump, so that in any additional cooling that needs to happen, we've got the proper temperatures in order to get the right oil temperature to the compressor. So then we come out here and we kind of tee off into two lines. So this back line feeds your rear bearing on the motor, right? And then the front line feeds the front bearing, and specifically, more importantly, the journal bearing. We can go ahead and talk about that a little bit now. So one of the things that is real critical is these have they're not super tight parameter in the window on the oil temperature side, but it's not, you have to be really careful with it. So these machines, if I remember correctly, without checking the manual real quick, won't allow you to turn on until that oil is either 110 or 120. Anything below that, it will not allow you to function. I believe it's 120, that's what it is. So below 120 degrees, this machine is going to give you a low oil temperature indication, and it's going to be trying to run the oil heater until it gets above that. Now, that oil heater only runs when the machine is off, and it's trying to maintain that oil between 140 and 160 when the machine is off. Now, once we get the machine online, we want that sump to be able to maintain around 120 to 140 degrees is pretty typical. You just don't want to go below that 120 mark. The reason this is so critical and so important is because that oil at that temperature has a very specific viscosity, okay? And so it's what it's designed to, its lubricating parameters, everything that we need it to do and be in its life revolves around that set temperature range. Anything outside of that, it starts to become too thin or too thick in order to do the job we're asking of it. If everything was just standard ball bearing, it wouldn't be as critical, and many centrifugals use these, what are known as journal bearings, okay? So a journal bearing literally kind of uses the oil as the bearing seal, okay? So the oil gets pumped into the journal, and the bottom of the journal will have these kind of trough looking indentions kind of machined into it, and it'll have usually two oil ports there. Sometimes some of them may have a third one on top, but most of the time you'll have two on the bottom. And so that oil gets pumped into that lower port or portion, and that's what is helping kind of lift the shaft. And also it's designed in such a way to when that oil gets pushed in there, it literally creates a oil ring that separates the actual steel shaft from the aluminum bearing. And so most of those journal bearings will tend to be an aluminum material, which is not going to take a steel shaft coming into contact with it with any grace. It's going to be very upset with you for doing so. What is critical there is that we've got to maintain the oil within those set parameters so that we make sure that that journal bearing functions properly, so that it doesn't cause any damage. The worst thing we could have happen is that journal bearing not lubricate like it needs to, and then that steel shaft comes into contact with that aluminum housing and just tears it to shreds. And you'll always know that whenever you go to do an overhaul. You'll pull that journal bearing out, and it'll be reamed out inside. I mean, it'll be, usually it's just pretty obvious. It'll have a bunch of scarring and all kinds of things because that shaft was able to constantly be making contact. So just side note, but something to be aware of, is that is very critical, and it does exist. Regardless, moving on from there. This port here, this is the oil return for the front bearing assembly. This is the oil return for the rear bearing assembly coming into this little oil separator. Again, the purpose of this is to take any refrigerant that gets trapped in the oil, allow it a place to release so that it doesn't make its way into the sump. Some of it will. That's why we have a vent on the tank itself, but we're trying to prevent as much as possible. From there, the oil just gravity feeds down back into the sump, and then back through the pump, and out it goes, whole 9 yards. That is the basic makeup of your oil management side of the system. Let's talk now about oil return and oil management. So there's 3 points of oil return that this machine goes through, and they do reference to these as eductors. Okay. Again, I'm not an expert on the eductor theory or design. I just know that it exists, and I try my best to work with it. Regardless, the first stage eductor is right here, coming right off the bottom of the sump. Its job is to just try to pull any oil or any oil that will collect in this portion of the system. Oil is heavy, and so it's going to fall towards the bottom. So any oil that is allowed to make it to this point, this eductor's job, or this return line's job, is to try to draw that oil back into the sump. This coming off the bottom of the evaporator here is your secondary, or your second stage eductor. And again, its job is to take any oil that collects in the bottom of the evaporator and draw it back into the condenser, or the oil sump itself. So this is the first stage, this is the second stage. All of these are doing the same basic job. There is a little filter type device that this goes through. And it's just all part of that draw sequence. Again, I'm not going to even pretend to try to explain the science behind it. I'm just going to tell you that it exists. And then this is the third stage here, coming off of the condenser. Okay. So we've got 3 different pipes. All 3 pipes' job is to do its best to get any oil that doesn't get trapped here. And how this happens is basically the discharge line. There's some of the oil is going to get grabbed by the refrigerant stream in the compressor, and it's going to get sent out the discharge. Okay, so when that happens, the most common points for that oil to be collected in is going to be this evaporator assembly, and then coming into this suction line. And then, again, they're trying to pull vapor off of the refrigerant, and to process that oil back out of it and get it back into the oil sump. This is a very common issue that a lot of people deal with. I've come up on several machines in this second stage line here. It'll have a ball valve on it many times, or a service valve of some sort, and it will be closed, right? So you have to be very careful of that and be mindful of that. And you don't want to just start pumping oil into these machines. Depending on the load conditions, it's very common for the oil to have migration issues on these. And when that happens, that oil had to have gone somewhere. If you don't see it sitting on the ground in front of you, it's somewhere in the system, right? And so we need to try to do our best, whether it's get a high enough load on the machine, make sure that the return lines are all open properly, something to try to attract that oil back into that tank and get it. There's a gentleman I've been working with over the last several weeks. If you don't know, you're welcome to reach out to me through my Facebook page at HVAC Time on Facebook, and reach out to me through the messenger there, and I will do my best to try to give you any tech support that I can on whatever equipment you're working on. If it's something I can't help you with, I'll just tell you, hey, I'm sorry, but I'm not going to be able to do much for you on this. Regardless, we and him have been working through a situation he was going through, and he ended up finding that he had a valve that was having issues. And if I remember correctly, it was the vent valve coming off of the separator, it was not opening properly, if I remember correctly. I'd have to go back and read back through our discussion. I'm trying to pull off the top of my head now. Anyway, point is, he was having an issue with the machine. Came in, they got it installed, they started it up, and it just, all the oil disappeared. And you know, that was because the oil return side of the system wasn't functioning properly. He had a valve that wasn't working right, and it was causing the oil to not get returned back to the sump. You know, just it's very, very critical that you keep up with this side of the system. One of the things that I have not discussed, and this is number 14 here, this is the purge assembly. This purge assembly's job is just to, because again, these are low pressure machines. R11 and 123 are low pressure. They operate inside of a vacuum. They are not positive pressure or high pressure machines like 134, R22, 410A, blah, blah, blah. Because they operate in a vacuum, they do allow a lot of atmosphere that has a tendency to, you know, seep its way into the system. And so it's routine and common that this purge assembly just has to occasionally kick some of that out of the system. This purge assembly is a video in and of itself, and just kind of giving its breakdown, its function, its purpose. This video is already getting long enough, so I'm not going to go in depth into that here. I will plan to do another video on that at a later date and time, and kind of talk about the regen tank and some of the different changes that have been made to those over time. Right now, Trane is the only one that I'm aware of, that I can think of, that is still using low pressure machines. I do know that York is going to be, if they haven't already announced it, they will be releasing a low pressure lineup again in the coming years. A couple of years, I think, was the last conversation I had with one of their factory guys. So we'll see what that lineup does. And obviously, if it's a low pressure machine, it's going to have a purge assembly to manage atmosphere and things in the system. But I do have a lot of videos already out there on the purge assembly. Regardless, I won't talk anymore about it. I've talked enough throughout this video now, so we'll conclude it here. I really appreciate y'all sticking around watching this, and I hope you get a lot of benefit from it. You know, if you have any other types of videos like this, any specific in-depth, deeper trainings that you're really looking for, that would significantly help you in your process, your system, you know, or just your training, let me know, because, you know, there's a whole heart of what I'm trying to do here is I want to be able to provide you with the information that you need so that you can, you know, provide a better life for yourself, for your family. I really appreciate sticking around to the end of the video. Always make sure that we're putting in the time to our families as well. You know, this career path requires an immense amount of energy and everything from us, but we cannot lose the sight that we have to take care of our families at the same time. So just make that time. MTT is one of my slogans I've come up with over time, and just, we have to make the time. Time's never going to be there. We have to make it. Anyway, y'all stay safe this summer, and I will catch y'all in the next one.